Linear Algebra II, Lecture 5, Linear Maps. Let us start with the definition of a linear map, and before we can state the definition, let us describe the setup. Let V and W be two vector spaces. For the moment, let us fully write that V consists of the vector space V, the addition on V, denoted plus sub V, the multiplication with scalars, denoted dot sub V, and the zero element 0 sub V. And similarly, W consists of the W, addition on W, multiplication with scalars for W, and the zero element 0 sub W. Definition. A map F from V to W is called linear, provided that it satisfies the following two conditions. Condition 1. The image under F of the sum x plus y of two arbitrary elements x and y in V is equal to the sum of the images f of x and f of y. Please note that x and y are added in V, while their images are added in W. So on the left-hand side we have plus sub V, and on the right-hand side we have plus sub W. This is the first condition, and the second condition is that the image under F of the element lambda dot x, where lambda is an arbitrary real number and x is an element in V, so this image should coincide with the element lambda times the image of x under F. And here also note that lambda dot x is taken for the vector space V, while lambda dot the image f of x is taken in the vector space W. So we have dot sub V on the left-hand side and dot sub W on the right-hand side in this equality. There are various ways to describe these conditions. So one usually says that F, a linear map F, preserves the vector space structures or intertwines the vector space structures or is compatible with the vector space structures. And in order to simplify notation, in what follows we will skip these subscripts V and W from the notation, but in each case it's very easy to determine which addition we are talking about or which multiplication with scalars or what kind of zero element do we have. Let us now give a number of examples. Example 1, consider the zero map 0 from V to W. So the zero map is defined in the following way. The image of any element in V under the zero map is the zero element in W. So in particular, for any two elements x and y in V, we will have that 0 of x is equal to 0, 0 of y is equal to 0, and 0 of x plus y is equal to 0. Therefore, 0 of x plus 0 of y is equal to 0 plus 0, which is 0. And this is equal to 0 of x plus y. So this shows that the first condition is satisfied. Similarly, for any element x in V and for any real constant lambda, we have that 0 of x is equal to 0 and 0 of lambda dot x is equal to 0. Therefore, lambda dot 0 of x is equal to lambda dot 0, which is 0, and this is equal to the image under 0 of lambda dot x. And this shows that the second condition is satisfied. Therefore, the zero map is a linear map. And this is true for the zero map between any vector spaces. Example 2. Consider the identity map from a vector space V to itself. So this map is defined the image of any element V in V under the identity map coincides with the original element small v. Now we can compute. So if we have any pair of elements x and y in V, so the image of x under the identity is x, the image of y under the identity is y, and the image of x plus y under the identity is x plus y. So therefore, the identity applied to x plus the identity applied to y is equal to x plus y, and this is equal to the identity applied to x plus y. So the first condition is again satisfied. Similarly, for any element x in V and for any real number lambda, the image of x under the identity is x, and the image of lambda dot x under the identity is lambda dot x. Therefore, lambda times the image of x is lambda x, and this is the image of lambda x. So the second condition is also satisfied, and this means that the identity map is a linear map. Example 3. We have already seen previously in the previous lectures that one specific map is linear. We just need to recall this. And we are talking now about the coordinate map. Let V be any vector space of dimension k, and let V, bold V, be a basis in V. Then we have defined the coordinate map with respect to this basis bold V, which takes an element x in V and maps it to the vector of the coordinates of x with respect to the basis bold V. And this vector of the coordinates is an element of r to the power k. And we have seen that the coordinates of the sum of x plus y with respect to V are equal to the sum of the coordinates of x and the coordinates of y for any x and y in V. And we have already seen that the coordinates of lambda x with respect to V are equal to lambda times the coordinates of x with respect to V for any x and for any lambda. So this means that the coordinate map is a linear map. Example 4. Matrix multiplication. Let V be the vector space R to the power n, and W be the vector space R to the power k. And let us fix some matrix A with k rows and n columns. So it's k times n matrix with real coefficients. Then we can consider the map F sub A from Rn to Rk, which is defined by taking the vector x in Rn and multiplying it on the left with the matrix A. So since A has k rows, the outcome will be a vector with k entries, which means an element in Rk. And using the usual properties of matrix multiplication, we can compute that F sub A applied to x plus y is by definition equal to A times x plus y, but matrix multiplication is distributive, so this is equal to ax plus ay, and this by definition equals fa of x plus fa of y. And this is true for all x and y from Rn. And we similarly have fa applied to lambda x is equal to a times lambda x, but since scalars commute with everything in matrix multiplication, this is equal to lambda times ax, and ax is fa of x. And this is true for any x in Rn and any lambda in R. So both conditions in the definition of linear map are satisfied, which means that F sub A is a linear map. Example 5, derivative. Consider V is equal to W to be the vector space of all real polynomials of degree at most k. Consider the map delta from this space to itself, which is defined in the following way. It takes a polynomial f of x and it maps it to its derivative f prime of x. Then the usual properties of the derivatives can be used to check the linearity of this map. If we apply delta to f plus g, then we need to take the derivative of f plus g. But we know that the derivative of a sum is equal to the sum of the derivatives. So we will get f prime plus g prime, and f prime is delta of x, and g prime is delta of g. So the first condition in the definition of a linear map is satisfied. Similarly, delta applied to lambda times f is equal to the derivative of lambda times f, but this is equal to lambda times the derivative of f because of the usual properties, and this is equal to lambda times delta of f for any f and for any lambda. Consequently, the map delta is a linear map. Example 6. Multiplication with some element in the polynomial algebra. Let V be the vector space of all real polynomials of degree at most k, and W be the vector space of all real polynomials of degree at most k plus 1 for some k. Consider the map M from Rx sub k to Rx sub k plus 1 defined in the following way. M applied to the polynomial f of x is equal to x times f of x. So we take f of x and we multiply it with x. And this is true for any f from Rx sub k. Then the usual properties of multiplications of polynomials can be used to check the linearity conditions. So if we apply m to f plus g, we will get x times f of x plus g of x. But multiplication is distributive, so this is equal to x times f of x plus x times g of x. But the first summand is m of f of x, and the second summand is m of g of x. And this is true for any f and g. And similarly, m applied to lambda times f is equal to x times lambda times f, but this is equal to lambda times x times f, and this is equal to lambda times m of f. And this is true for any f and for any lambda. So this shows that the map M is linear. Example 7. Rotation in R2. Let V and W be the usual real plane R2. Fix some angle phi and denote by R phi the map from R2 to R2 given by the counterclockwise rotation with respect to origin. So here is the illustration of this map. If we take any vector v in R2, so we rotate it counterclockwise by the angle phi, and we get the element R phi of v. And from plane geometry we know that rotation applied to the sum of two vectors is equal to the sum of the images of these vectors under this rotation, and similarly R phi applied to lambda times x is equal to lambda times R phi of x. And this means that this rotation is a linear map. Some more geometric examples. Example 8, projection in R2. Consider again the vector space R2 and fix some line L in this vector space which goes through origin, and denote by P sub L the projection of a vector on this line. So here is an illustration. We have our vector space R2, we have the line L, and we take the vector V, we take the endpoint of this vector, draw the line which is orthogonal to L, and now we get the vector PL of V inside this line. So this is the projection of the vector V onto L. Also, one can say that this is the orthogonal projection of V onto L. And from plane geometry, we know that PL applied to x plus y is equal to PL of x plus PL of y. And similarly, PL applied to lambda x is equal to lambda times PL of x. So such projection is a linear map. And similarly, one can also see that the projection onto a plane in R3 is a linear map. One more example, example 9, and this is the reflection in R2. Again, the same setup as in the previous example. So we have the plane R2 with a fixed line L, which goes through origin, But now we use this line as a mirror to define the map SL, which takes an element V and reflects it into this line L as if L is a mirror. So we draw this orthogonal line from the endpoint of V to L, and then we go past L and take here the vector of the same length as between L and V, but on the other side. And then we have this vector S sub L of V, which is a reflection of V with respect to the mirror L. And again, from the plane geometry, we know that reflecting the sum of two vectors, we will get the sum of their reflections, and reflecting lambda x, we will get lambda times the reflection of x, which means that this is a linear map. And similarly, the reflection in some plane in R3 is also a linear map. So here is one non-example, so a map which is not linear. So let V and W be just the one-dimensional vector space of real numbers, and consider the map F from R to R, which is defined in the following way: f of x is equal to x squared. Then f of 1 plus 1 is equal to f of 2, which is 2 squared, which is 4, while f of 1 plus f of 1 is 1 squared plus 1 squared, which is 2. This should be 2. In particular, f of 1 plus 1 is equal to 4, and this is not equal to f of 1 plus f of 1, which is equal to 2. So 4 is not equal to 2, so the first condition is not satisfied, and therefore the map F is not linear. So a natural question is how to work or compute with linear maps, or maybe more specifically, how to describe a linear map in such a way that computer can understand it and work with it. And the answer to this question is that we need to use the matrix of a linear map. So what is the matrix of a linear map? So let V and W be two vector spaces. Let F from V to W be a linear map. Choose a basis bold V consisting of V1, V2, and so on Vk in V, and also choose a basis bold W consisting of W1, W2, and so on Wm in W. So in particular, the dimension of V is k, and the dimension of W is m. Then, for each j from 1 to k, we can take the basis vector Vj in our basis bold V and apply our map F to it. We will get an element F of Vj, and this is an element in W. And since this is an element in W, then we can look at the vector of the coordinates of this element with respect to the basis bold W. And if we collect all these coordinates into a matrix, this matrix is called the matrix of F with respect to or in the basis bold V and bold W. So the matrix of F in these bases is defined as follows. So the first column of this matrix is exactly the column of the coordinates of the element F applied to V1 in the basis bold W. The second column of this matrix is the column of the coordinates of the element F of V2 in the basis bold W, and so on. So the matrix has k columns, exactly as many columns as we have elements in the basis bold V. Why is this a useful notion? So here is the main property of the matrix of the linear map. For any element x in V, the coordinates of the element f of x, so this is an element in W, so we are talking about the coordinates of this element with respect to our basis bold W. So these coordinates can be computed as a product of the matrix of the linear map F in the basis V and W times the coordinates of the element x in the basis bold V. So using the matrix of the linear map, we can compute coordinates in the target vector space, knowing the coordinates in the original vector space. Proof. Assume that the coordinates of x in the vector space V are lambda1, lambda2, and so on, lambda k. Then we can compute f of x in the following way. So x is equal to the sum over all j of lambda j times vj. This is just the definition of the fact that lambda j's are the coordinates of x. But now f is a linear map, so we can commute it with the sum and with all these scalars. So we will get the sum over all j, lambda j times f applied to vj. But f of vj was something which we used to define the matrix of the linear map. So we know that f of vj is, by the previous slide, the sum over all I, and then aij times wi, because aij's are exactly the coordinates of f of vj in the basis bold w. So now we can change the order of the summation and rewrite it as a sum over all i's of wi with the coefficient sum over all j, lambda j times aij. But this is exactly the definition that this expression, the sum over all j, lambda j, aij, is exactly the i's coordinate of fx, because fx is written as a linear combination of the elements in our basis bold w. And now we can simply check that this expression exactly coincides with the i's entry of this product. So this is the matrix of our linear map by definition. These are the coordinates of x in the basis bold V. And if we multiply these two matrices and look at the i's component, we will have ai1 times lambda1 plus ai2 times lambda2 plus and so on. This is exactly this expression. And this proves our theorem. Let us now look at some examples. Consider the zero linear map from V to W. Choose any basis in V and any basis in W. Recall that the zero map is defined as follows. It sends everything to zero. In particular, all elements Vj in the basis bold V are sent to zero. So the coordinates of the zero vector in basis W are zeros. Consequently, the matrix of the zero map is the zero matrix. It has as many columns as the dimension of V and as many rows as the dimension of W. Example 2. Consider the identity linear map from V to V. Choose any basis V in V, and since our domain is equal to the target vector space, then as a basis W, we automatically get our basis V. Then the identity map, it sends V sub j to V sub j for any j, and in particular, the coordinates of Vj in the basis V are almost all zeros except for the one at position j. And if you write this into the matrix, so the first column will have 1 in the first position, the second column will have 1 in the second position, and so on. So the matrix of the identity linear map in any basis is the identity matrix. Example 3. Consider the derivative linear operator from the vector space of all polynomials of degree at most 3 to itself. The standard basis in this vector space consists of the polynomials 1s, x, x squared, and x cubed. So the derivative of 1 is 0, the derivative of x is 1, the derivative of x squared is 2x, and the derivative of x cubed is 3x squared. So the matrix of this operator in the standard basis is as follows. So the first column is 0, because we have 0 here. The second column is 1, 0, 0, 0. The third column we have 2x. This is 0, 2, 0, 0. And the last column we have 3x squared. So this is 0, 0, 3, 0. So this is the matrix of the derivative. Example 4. Consider the counterclockwise rotation r phi by the angle phi in r squared in the real plane. In the real plane, we have the standard basis consisting of the vectors e1 and e2. So e1 is a horizontal basis vector and e2 is a vertical basis vector. And here is a computation of the images. So if we apply r phi to e1, we take the horizontal unit vector and rotate it by phi counterclockwise. The obtained vector, by definition, has as the first coordinate the cos of phi and as a second coordinate the sine of phi. So these are the definitions of cos and sine functions. So the first column of the matrix consists of cos phi and sine phi. And now if we take the unit vertical vector e2 and rotate it counterclockwise by phi, we will get a vector which has as the second coordinate now cos phi and at the first coordinate sine phi, but in the opposite direction, so it will be minus sine phi. Consequently, the matrix of the rotation r phi in the standard basis, when we read it column-wise, is the 2 times 2 matrix cos phi, sine phi, minus sine phi, and cos phi. Example 5. Consider the matrix A, which is a 2 times 2 matrix 1, 2, 3, 4. And consider the linear operator f sub A on the space of all 2 times 2 real matrices, which is given by the left multiplication with this matrix A. So in the vector space of all 2 times 2 matrices, we have the standard basis consisting of the identity matrices E1, 1, which has 1 in position 1, 1, and the rest is 0. Then we have E1, 2, which is a matrix 0, 1, 0, 0. E2, 1, this is a matrix 0, 0, 1, 0. And the matrix E2, 2, which is 0, 0, 0, 1. So let us compute the images of these matrices under Fa. So Fa applied to E1, 1 is equal to A times E1, 1, which is the product of 1, 2, 3, 4 times 1, 0, 0, 0, and this is 1, 0, 3, 0. Fa of E1, 2 is equal to A E1, 2, so this is the matrix A times the matrix E1, 2, and this is equal to the matrix 0, 1, 0, 3. So similarly, Fa applied to E2, 1 is A times E2, 1. Here is this product written as matrices, and this product equals 2, 0, 4, 0. And finally, Fa of E2, 2 is A times E2, 2. Here is this product as matrices, and we get 0, 2, 0, 4. So now when we write the coordinates of all these 4 matrices which we got as columns, we get that the matrix of the linear operator Fa in our standard basis is the following matrix which we read column-wise: 1, 0, 3, 0, 0, 1, 0, 3, 2, 0, 4, 0, 0, 2, 0, 4. Let us finish with some problems and questions. Question 1. Check that projection onto a plane in R3 is a linear operator. Question 2. Check that reflection with respect to a plane in R3 is a linear operator. Question 3. If f from V to W is a linear map, then how many rows and columns does the matrix of f have? Question 4. Determine the matrix of the counterclockwise rotation by the angle pi divided by 2 in R2. And question 5. Determine the matrix of the linear operator f from Rx sub 2 to Rx sub 3 which is defined as follows. So the image under f of the polynomial f of x is equal to minus 3x f of x plus x squared f prime of x minus f2 prime of x. Thank you very much and see you next time.